Hello and welcome to The Explainer. We're all about breaking down big, complex topics into something you can really wrap your head around. So, have you ever just stopped and wondered about the actual shape of things? I mean, on a molecular level. Like, why is a water molecule, H2O, bent like this? And then, at the same time, a carbon dioxide molecule is a perfectly straight line? It seems kind of random, right? Well, it's not. The answer is hidden in the invisible forces that glue atoms together. And today, we're going to pull back the curtain and see what the rules are. Okay, let's get into it. So it all starts with something really basic that every single atom wants: stability. You could say atoms, kind of like us, are always looking for their most comfortable, low-energy state. And this whole quest for comfort is governed by something called the octet rule. It sounds technical, but honestly, you can just think of it as the rule of 8. An atom is at its happiest, its most stable, when its outer shell is packed with 8 electrons. So to hit that magic number 8, atoms will do pretty much whatever it takes. And that usually means they've got to team up with other atoms to either gain, lose, or most often share electrons. So how does this teaming up work? Well, one of the most common ways, and the one we're going to focus on, is by sharing. This is the foundation for most of the molecules that make up our world. This sharing creates an incredibly strong connection called a covalent bond. It's basically a molecular handshake. See, by sharing electrons, both atoms get to count those shared electrons toward their own magic number of 8. It's a win-win that holds the whole molecule together. Let's take methane, that's CH4, as a perfect example. You've got a carbon atom that needs 4 more electrons to be happy. So it finds 4 hydrogen atoms, and each of them just needs 1 more. They all agree to share, and boom, everybody wins. Carbon gets its full set of 8, and each hydrogen gets its 2. Total stability. But here's where it gets really, really interesting. Just sticking together is not the whole story. The final 3D shape of a molecule all comes down to how those electrons are arranged, and it's driven by one simple, powerful rule. They all push each other away. The absolute key principle here is that all the groups of electrons hanging around that central atom repel each other. I love this analogy. Think of a bunch of balloons that you've tied together at the knot. What do? They automatically spread out, right? They push on each other to get as much personal space as possible. Electrons do the exact same thing. And of course, there's a fancy scientific name for this: VSEPR Theory. It sounds super complicated, but let's break it down. It stands for valence shell electron pair repulsion. Valence shell is just the outer shell of electrons, the ones doing the bonding. So the whole thing is just a fancy way of saying electrons in the outer shell push each other away. That's it. Now, here's a crucial twist. Not all electron groups are created equal. On one side, you have bonding pairs. These are the electrons locked into a bond between 2 atoms, so they're pretty well behaved. But on the other side, you have the lone pairs. These guys are the real bullies of the molecular world. They aren't shared, so they take up a ton more space and have way more repulsive power. So get this. If we can just count the number of electron groups around an atom and keep track of which ones are the bullies, we can become molecular architects. We can literally predict the exact 3D shape of a molecule before we even see it. Okay, let's put this theory to the test. Let's go all the way back to our first puzzle, carbon dioxide. We've got the central carbon atom bonded to 2 oxygens. That gives it 2 electron groups. And, this is the important part, it has 0 lone pairs. No bullies. So with no bullies pushing them around, what do those 2 groups do? Well, to get as far apart from each other as possible, they fly to opposite ends of the atom. And that creates a perfectly straight, linear molecule with a 180-degree angle. Puzzle solved. But now, let's look at water. Water is a completely different story. The central oxygen atom has 4 electron groups swirling around it. But here's the catch. 2 of them are bonding pairs connected to hydrogen atoms, but the other 2 are those big, repulsive, bully lone pairs. And what do those powerful lone pairs do? They flex their muscles. They take up a ton of space, and their massive repulsion shoves the other bonds, the ones with the hydrogens, and squishes them closer together. And that powerful downward push is exactly what forces the water molecule into its famous bent shape. And what's so cool is that this works for everything. Check out this table. It just lays it all out. For CO2, 2 groups and 0 lone pairs, you get a line. For ammonia, NH3, You have 4 groups, but one is a lone pair, a single bully, which pushes the others down into a pyramid. And for water, 4 groups and 2 bullies give you that bent shape. It's really just a simple counting game. So the big takeaway here is that the wild, complex world of molecular geometry isn't random at all. The incredible variety of shapes that build literally everything around us all comes down to a few simple, predictable rules. Everything just emerges from these fundamental ideas of wanting stability and pushing each other away. It really makes you wonder, doesn't it? What other huge, complex structures out there in the universe are also governed by such simple, elegant rules?